In this tutorial, we'll get to know our laboratory of ion beam methods which we have available. The Tandretron accelerator supplied by the Dutch company High Voltage Engineering was installed in a new hall adjacent to the Van de Graaff accelerator facility in Res near Prague. The accelerator was put into operation in November 2005. Tandretron is used for production of ion beams with energies in the range from 400 keV to 30 MeV of almost all elements of the periodic system. The produced ion are used for the ion beam analytical methods and for modification of solids properties. It is the medium current version with a terminal voltage varying from 200 kV to 3 MV. The accelerator is equipped with 3 ion sources, which are electrically isolated from the accelerator and operate at a voltage of 20 kV. From the ion source, the particles move through the ion optics to the magnet. In the magnet occurs to selection of the desired element. From there the ions go to the low-energy part separated from the high-energy part by the high-voltage terminal, where a gaseous stripper is incorporated. The ions lose electrons, and changed from a negative to a positive charge state. These partially accelerated ions continue to the high-energy part. The ion beam is directed into a switching magnet, which bends ions of specific charge state and energy, into one of 5 defined beam lines and chambers. When charged particles penetrate through the solid material, several phenomena can occur like elastic scattering, elastic recoil or knocked out electrons. Ion beam analytical methods are based on monitoring of products of the given phenomenon. Rutherford backscattering spectrometry is a non-destructive ion beam technique. The sample is during the RBS analysis irradiated by light-energetic ions, usually alpha particles or protons, then the elastically backscattered from nucleus inside the analyzed solid and subsequently detected at large angles. Energy of use ions during RBS is in order of MeV. The mass of the target atoms could be identified from the energy of the backscattered projectile. The backscattered particles are detected by the semiconductor detectors and thus we obtain the typical RBS spectrum. RBS is unique in that it allows quantification without the use of reference standards and elemental depth profiling, but it is limited by low sensitivity to light elements. RBS can be used for compositional thin film analysis, determination of the areal concentrations, elemental depth profiling and determination of the film density of the amorphous material. In a special arrangement, it can also be used in the characterization of crystalline materials. Such a method is called Rutherford backscattering spectrometry in channeling mode. Elastic recoil detection analysis is a method which uses heavier ion than target atom to recoil low-mass target atoms and to measure their depth profiles. The ion projectile need only have a mass greater than the target atom. Alpha particles are commonly used to obtain recoil spectrum for hydrogen and its isotopes. The ERDA is a complementary method to RBS that allows for the depth profiling of light elements, such as hydrogen and deuterium. This method is particularly useful in various scientific and industrial applications, including material analysis, depth profiling, thin film analysis, or material development. Particle-induced X-ray emission is non-destructive method in which X-ray emission is used for elemental analysis. The high-energetic proton beam excites, due to inner shell ionization, the emission of characteristic X-rays from the sample atoms. In the true sense, PIX is not a nuclear technique, since the ionization of the atoms by the ion beam and the subsequent emission of characteristic X-rays are purely atomic electromagnetic processes. Limitations of this method is not allow for the depth profiling in a single measurement, as the information about the elemental concentration is integrated over the entire analyzed depth. Particle-induced gamma-ray emission is complementary method to PICS and uses nuclear reactions induced by MeV proton beam. Typically, an MeV proton beam is directed onto a sample which may be tens of microns thick, and the fast protons may excite the target nuclei such that gamma rays are emitted. These method may be used to characterize the sample. Particle-induced X-ray emission and particle-induced gamma-ray emission are used in various fields, particularly in the analysis of the elemental composition. Typical samples are aerosols, biological materials, minerals, tissues, or art and historical objects. Microbeam method involves using highly focused beams of particles or radiation to analyze and manipulate materials at very small scales. Limitations of this method is slightly lower detection limit compared to broad beam due to lower beam current. This method have a wide range of applications across various fields. For instance, can be used for mapping of thickness of samples or for microstructuring of material in the preparation of condensators. The main advantage is that ion implantation allows for very quick and easy modification of solid materials. It gives us the ability to precisely dope materials or create controlled defects in crystals, which is essential for tailoring their electrical, mechanical, or optical properties. However, there are certain limitations we must consider. There is always a risk of radiation-induced damage of the sample. For sensitive samples like polymers, we have to be very careful about the potential for thermal degradation during the process. In terms of specifications, our system can work with elements from hydrogen up to gold, excluding inert gases, lanthanides, and radioisotopes. We typically operate within an energy range of 0.6 to 30 MeV. Through the utilization of ion implantation in glass, crystals, polymers, or 2D materials, we have the capability to generate optical waveguides, introduce nanoparticles into the material, create nanostructures, or alter the surface of the sample. Such processes can result in the modification of electrical, structural, and optical properties. Thank you for your attention.